Okay, so today I want to go over how to trace some of the operations with ttnn. Basically, it allows you to sort of see what's actually like the flow of the tensors into specific hardware, whether or not tensors are going to go into CPU memory or wormhole memory, pretty much. API seems pretty simple. We just use this whole ttnn.tracer.trace helper, wrap our operations like around this with block, and then we can just output some visualization using the visualize method provided from the ttnn tracer. So yeah, I just want to be able to show you guys some examples, and I think we need graph viz for this. So I don't really remember how I did that. I think I just did sudo apt install graph viz, and then should go. Oops. So like I think that's like the only dependency that's necessary. I already have that installed. So if you want to get this example running with output on some of the images that the tracer will output, just basically install this GraphViz thing first. Okay. Okay, so let's work through this slowly. Build up some examples and just see. So I think the first thing is that let's just create a notebook, a new notebook, and then we'll do all our examples in this new notebook. So I'm going to save the notebook right away. And I'll call this 03 tracer example. Okay. Okay. So documentation says what? That we do need to set some sort of environment variable. I know that we do. So let's look at tracer, ttnn tracer in the tutorials right here. So if we look at this basic tutorial, we do need to set this environment variable here called ttnn config overrides. And then there's a key here that looks for called enable fast runtime mode. We'll set to false, and I think that just kind of puts things into like debug mode. So things will be a little bit slower, but at least you'll be able to see what's going on. Okay, so we'll just add that into our first cell here, and we'll execute that. We'll choose Python environment, okay, 3.10 in our virtual environment. So we've set our environment variable ttnn config overrides to have this specific JSON value here. Looks like JSON. It's called enable fast runtime mode. We'll set that to false. Okay, so this is actually just a straightforward tutorial, it seems like. So we'll just need to import some of these necessary libraries here. For this example, let's just import torch ttn and then the ttn tracer code. So if I tuck this aside here and then just kind of bring this here to the other side, I can just say, well, import torch, import ttnn, and then from ttnn dot tracer import trace and then visualize. Okay, I suspect that's all we will need for this example. I think this one will kind of just give some basic examples. Okay, so with this first example here, it looks like there's a torch tensor created with some random integers. Shape looks like it's 1/64. So then it shows up in this graph here. And then you basically want to throw this into a torch dot exponential function, right? So then you put this into this as input, this torch.exp, and then output is a torch float32 tensor. Okay, so this is just torch. So this, it seems like this works with not just ttnn, but it also works with torch tensors too. Now, this example here shows tracing torch functions and ttnn operations. So again, we create a torch tensor. We convert that torch tensor to a ttnn tensor. And then we do a reshape. And then finally, we convert it back to torch tensor. So convert the ttnn tensor back to a torch tensor after reshaping it. So what's the flow here? So we create the torch random integer tensor, and this time it's 4x64, which is consistent here. You call the from torch function. So what you're going to see on the side here is going to be the function call. Input is at the top, output's at the bottom, so it's kind of flowing down directionally. You'll see that for ttnn tensors, you'll have more information about, such as the data type, uint32, and the layout of the specific tensor. So you can already kind of start to see how this would be a good debugging tool. So after we get this output, well, we call ttnn.reshape, like we did here, with this tensor as input, and then this shape as another input. So we see here, input 0 is a shape. Oops, where is it? Right here. Right here. Shape of 4x64, right? With that tensor in. Okay. And then we'll output a new tensor that's 2x4x32, which we specified here. Okay, so reshape. So reshape's right here. Now after that, we convert the ttnn tensors back to a torch tensor with a toTorch method call, and we'll see that here. So notice how the input tensor is uint32, and then our layout is row major, so that tells us that it is a ttnn tensor. Output now looks different. It's now a torch tensor, a torch int32, and the layout is strided. So before I couldn't recall what the layout of a torch tensor was. I think I said slided or something like that, but it's actually strided. I thought it was like a sliding thing, but it's actually called strided. Anyway, so yeah, that's just basically the pattern here. The tutorial just goes through how to do that same thing over and over again. So eventually you can kind of chain a bunch of things together. You see how this one is like super long. And then what comes out is this like crazy graph of operations here. But I don't know, it could be useful, right? You can see exactly where your tensors are going into. Yeah, there's more, but today we just want to do the tracer. So I want to go back and demonstrate this tracer code in a familiar operation. That's going to be the matrix multiplication. So I'm just going to create two tensors and then just multiply them together and visualize that. And I think that gives us a gist of how we can use this, at least this tracer at a very basic level. So if I wrote with trace here, as with the documentation example, I could create a tensor A. So I use ttnn dot from torch. So I'm just going to create a ttnn tensor from torch. I'll just create a torch tensor. A torch tensor that is maybe consisting just of one single row of 3 and 3. And then I can specify the D type in this case. Specify the D type in this case to be, I guess, bfloat 16. So ttnn dfloat 16. It's still an integer, but whatever. Layout can just be directly as a tile layout. And I could create like, I could also create a tensor B. In this case, this one is going to be, let's say, 2 rows with 1 column each. So it's going to be a 5 as 1 row, and then 4 as another. And then let me see if I can match this up correctly. Okay, So D type is going to be ttnn.bfloat16. Layout is going to be tile layout again. Okay, so now we have basically our two tensors we've created under the with trace. Okay, oops, D type must be torch. Oh, parentheses. Yeah, for sure. I have way too many parentheses. It's supposed to be like this. There we go. Tracing's already enabled. Okay, you know what? Let's restart this because I executed things twice. So there we go. Okay, so you can see that it does have a lot more information when you turn on this tracing. Let's not worry about that just yet. Let's just see the behavior. So let's say we want to just visualize what tensor A looks like. So we had created these two tensors under trace, right? And visualize takes in a tensor as an argument. Okay, so let's try visualizing those two tensors. Okay, we want to visualize A and B. So we can just type visualize A, visualize B. And if we did that, we can actually dump the graph of both A and B. So remember we said A was a tensor that was one row with two columns. So we'll see that here where we did a from torch, right, as input 0. And what comes out is a ttnn tensor with bfloat16 type with a tile layout. Similar with tensor B, we had a tensor created from torch that was 2 rows, 1 column each. Starts out as an int64 by default. Then we threw that into the ttnn from torch. Out came out a bfloat16 ttnn tensor with a tile layout. Okay. Now, in order to do the matrix multiplication, we need to grab a device handle, meaning that we had to now open the device with ttnn. So again, as you are familiar with this pattern, we could do device ID 0 because I only have one wormhole in my computer. I could just basically get that handle with ttnn.openDevice and then specify the device ID as an argument. Okay, so I've opened the device. Again, you'll know that it works if you have this familiar logging here available. And then what I want to do is I want to send A and B ttnn tensors to the device. But when I'm sending it, I also want to be able to trace those. So again, with trace, I'll just basically write the code to send A and B to the device. So I could do A equals ttnn dot to device with A as the argument of the tensor that I want to send to the device, and then the device I want to send it to, right? Same thing with B. Okay, so just do the same thing. And if I do that, I actually end up being able to send the tensors to the device. Okay, so time to visualize it and see what that looks like now. So visualize A, visualize B, execute that. And now it's interesting, right? Like, because we had the same flow as before. It keeps track of it. But now we see that we send, so we create the tensor from torch, okay? And then we convert the torch tensor to a ttnn tensor, but then we call toDevice right here, right? So toDevice with the tensor as an input. And now inside the device, we do have as an output a tensor that points to the one in the device. It's a bfloat16 type tile layout, and it's in DRAM. Okay, so it's in the device's DRAM, because the wormhole has like 2 levels of memory. One is like L1, and the other one is regular memory, regular DRAM. So same thing with this tensor here. Tensor B, right? We do the same flow. We had sent it to the device, and this is what it looks like inside the device. It's a ttnn tensor with shape 2 by 1. Data type is bfloat16. tile layout, and it's also living in DRAM. Okay, so next we want to multiply the matrices A and B using the ttnn mapmul function, and then output that as C. We'll want to also again trace all that. So with trace, okay, we'll do C equals ttnn dot mapmul with A and B, and then we can just execute that. And then you'll see a bunch of logging related to that mapmul operation. Okay, and then now let's actually visualize what C looks like. So we visualize C, we see that it came from tensors A and B at the very beginning as torch tensors. Then we call from torch on both A and B, output those into ttnn tensors with tile layout. Then we send them to the device. Then we use the tensors in device, these two here, and actually pass them as inputs to ttnn.mapmul. Okay. Now out comes a new tensor still in the device, right? As a 1x1 tensor, B416 tile living in DRAM. So we can just output that. And we'll see that it is a tensor that is 1x1 shape, right? 1x1 D-type B416 in tile layout. Okay, so now let's actually take this C tensor in the device and send it back to the CPU. So we could do C equals, let's trace it though, with trace, C equals ttnn dot from device. Okay, I think it's C, just simply C, like that. Yeah, so call from the device to send it back, and then if we visualize C again, what's happening now is you provide as input the ttnn tensor living in the device, in this case in DRAM, and just output it back out as a regular ttnn tensor. Okay, so B416 tile layout. So that's actually how you trace. Don't forget to close your device. So ttnn.close device. Device as the handle, and that's it. So yeah, relatively simple technique to trace where your tensors are going. It's a quick video today. Just wanted to show you that. Let's at least add some documentation so that we can refer back to it someday. So we could do tracer example. So this notebook shows us how we can trace and visualize a tensor, a ttnn tensor, through series of operations on it. Okay, and then we'll have to say if we want to use tracing, we have to configure the ttnn config overrides environment variable. We want to set the enable fast runtime mode property value to false. Okay. Next, let's have something to say. Well, import. How do we do this? Oh yeah. Oh, come on. Okay, yeah. Import the required libraries to trace. We need to import trace and visualize from the ttnn tracer module. Okay, and then let's say always wrap the tensors you want to trace within the with trace block. Then finally visualize the flow of your tensors by calling visualize, okay, with the tensors as input. Okay, open the device to grab a handle to it, send to the device, send the tensors to the device so that we can perform the ttnn mat mul operation. And then finally perform ttnn.matmul, visualize the results, and then send the tensor back to the CPU. Send the resulting tensor from ttnn.matmul back to CPU memory, and then visualize the entire flow. So we'll see visualize the entire flow of the matmul result. Okay, and then don't forget to close the device to clean up. Smiley face. Okay, that's it. Quick video today. We're just slowly building up some skills. We'll go through some of these tutorials formally, but this is enough to get us going for the next thing that we're going to do. So talk to you next time. Bye.